All right, everybody, this is part 4, Thursday's work. So we're looking at this, and this is where we finished yesterday, determining whether it's parallel, perpendicular, or neither. What are we doing now? We barely touched on it above the other day, but now we're going to get a little bit more into it. This is about transformations of graphs' parent functions, okay? Parent functions always start at the origin. And then whenever they move up, down, left, right, if they flip upside down, it all depends on the numbers that are either being multiplied, added, or subtracted to these particular equations. The easiest things that we noticed first is an upward or downward movement from it being centered at the origin. So this would be outside of the function, like y equals the absolute value of x. Absolute values are V-shaped graphs centered at the origin. This one has moved from the origin. So we have to say, did it go, first off, did it go up? Did it go down? Did it go left? Did it go right? Or maybe it flipped upside down. Okay, it's still a V-shaped graph pointing up, so it didn't flip upside down. It did not, the center or the vertex of it did not move off of the y-axis. So it's still has an orientation to the origin. What did happen to it? Well, it dropped. So this went down. How many units? 1, 2, 3. So it went down 3 units. Our first thing they want to know is, did it go up, down, left, right? It went down. Okay, so if it went down, we have to then say, okay, well, how many units did it go down? It went down 3 units. So if you were to write it, they're not asking us in this question to write the equation, but if it was going down, so outside of the function is a minus sign. And how many units? 3. Maybe y equals the absolute value of x minus 3. The next one, they want you to say, and you're going to do this one, okay? Take a look at it. What's going on? Did it move up, down, left, or right? How many units did it move up, down, left, or right? Always be careful when you look at your margins, guys. They may not always be going by 1, so do be careful. Next one again. So now they give you an equation, and they want you to say, hey, which one of these 4 graphs is correct? So I see, just by looking at it, I see 3 graphs that are pointing up, 1 that's flipped. We just said, remember, if it flips, it's because there's a negative outside. And we used our quadratic formula here as an example. X squared is a U-shaped graph pointing up. Negative x squared is a U-shaped graph pointing down. That multiplication of a negative out front makes it flip. So if we look at this one again, is there a multiplied -1 out front? No, so we know it can't be this one. It has to be one of these. These two have moved up and down. So this one moved up, this one moved down. This one moved to the right. So right-hand movements are subtractions inside of the function. There's nothing inside this function. It's just x. Can't be this one. So now we know it's either moving up or it's moving down. So we look at the symbols. The negative symbol there outside the function is telling us it's moved down. So it can't be this one. So even without really studying the graph, because this is tiny numbers, they're going by what, 2, 4, 6, 8, 10. They're going by 2s here. If you just look at this graph real quick, you say, oh, look, it moved down 1 unit. You're not looking that, they're going by units of 2 on this particular graph. But by slowly taking all the information you can decipher what's going on in these particular graphs. So C would be your correct answer. It says write the equation for the function, or for the following translation. Y equals negative x squared 9 units down. Okay, so first off, the negative x squared means we know that this is going to be an upside down V. And it's going where? 9 units. Where? Down. Down is a negative outside of the function. How many units did it go down? 9 units. Wow, there you go. So y equals negative absolute value of x minus 9. And we're not going to be doing 30. 30 will end up starting to go off to our next, I believe. Oh, no. We'll do it. I'll count this in this lesson. So we're going to start solving systems of equations. We have already been doing this a little bit, and it shouldn't be too bad. When we have a systems of equations, we have a couple of ways we can solve them. You can graph both of those, and the point at which those two lines intersect is the solution. That's your x-coordinate, and that's your y-coordinate. And it would make both equations true at that exact point, because it's the only point that they both have in common. The other two ways that we know how to solve these is that we can take these equations and we can use both of them together to help us solve it. We can either do elimination or substitution. So we could add the two equations together and try to cancel one of the variables. We're allowed to multiply the equations by any numbers we want to help us do that, as long as when we do, we multiply every single piece by the same number, so we're not altering the equation, we're just making it a larger value of itself. It helps us cancel it. Substitution. If we have one that's already set up like this one, says y equals this, you can say, well, I know the law of substitution says that if these two things, there's a relation here between these two. That's why there's this set notation here, okay? Substitution says, I know if y equals x plus 2, I can then take out this y here and plug in x plus 2. Now I only have one variable. I can solve for it. When I get whatever that value they say x equals, I can then take that x or that value of x and back substitute it into one of your original problems. Okay, we're going to do this particular problem both ways so that you can definitely see, and we'll do it every single way. We're going to graph it so you can see. We're going to do it by substitution. We're going to do it by elimination. Let's do the graph first, because everyone hates that. We have two equations that are already in slope-intercept form. Y equals mx plus b. Y equals mx plus b. M in the first one is 1. It's that invisible math in front, 1. So we know our slope for the first one is 1. Our y-intercept is 2. So we come over here to the graph, put a dot on 2. And then we are going to go what? The slope is a positive 1. So we go up 1 and to the right 1. Up 1 to the right 1. Up 1 to the right 1. And it's going to keep going and going and going and going and going. Both directions, because it's a line, it goes forever and ever and ever. I'll stop right about here because I don't think we need the whole thing. Now we have to do the next one. All right. See if I can get colors to change. For me, we have two lines, two separate colors. Our intercept is -8. So on the y-axis, -8. Put a dot. Oh, our entire other line disappeared. All right, let's do this one again real quick. 2. It's always when we try to use colors so we can make learning fun. Technology does not want to cooperate. Okay, back down, -8. And there's our intercept. And our slope here is -1, so it's going to go down 1 to the right 1. Down 1 to the right 1, which also goes in the reverse direction. And bang, right there is where we're going to end up having our intersection of this line. So we are intersecting right here at the point to the left. 1, 2, 3, 4, 5, negative 5. And then we went down 1, 2, 3, negative 5 comma negative 3. We just solved this system of equations by graphing it. Okay, let's now solve it by elimination. It's perfectly set up for elimination. Look at our variables. This is not easy to cancel. This one here is pretty much, look, they're a positive and a negative. You add them up, they go away. So y plus y is a 2y. And you have a negative 8 plus a positive 2 equals negative 6. Okay, so now we have to divide by 2. Divide by 2, and we get y equals negative 3. Look, it matches. So how do we find this x? So we have to take, if we know that y equals negative 3, we can take the negative 3 and plug it back into one of our original equations. So y, oops, we already have our y. Erase that. So we say y is negative 3, so negative 3 equals x plus 2. This x is not by itself, so subtract 2. Subtract 2. X equals negative 5. Great. That's elimination. We just did that by elimination. I draw a line here. Now we're going to do substitution. They're telling us that this is what y equals. Okay, y equals x plus 2. So I could take x plus 2 and stick it into the next problem where y is. I'm going to substitute it in. X plus 2 equals, well, what does it do? Negative x minus 8. Okay, I need to move this negative x here, so I have to add an x. I'm going to do two movements at the same time. I'm going to subtract 2. Okay, I had to add this x here too. So now I have a 2x equals negative 10. X is not by itself. Divide by 2. Divide by 2. X equals negative 5. Oh, look at that. Imagine that. Our x coordinate when we graphed it, it said it was negative 5. When we did it by elimination, it says it's negative 5. So now how do we find that y? We have to take this y or this x and back substitute it into one of the original problems to make sure that we have the correct y. So let's stick it into the first problem. Y equals, we're going to take out this x and put in a negative 5 plus 2. We evaluate and simplify. Y equals negative 3. Negative 5 plus 2. If you owe somebody 5, you take away, you pay them back 2, you still owe them 3. So here we go again. Exact same thing. Those are the 3 different ways to solve systems of equations. So the next one is going to ask you to solve the system of equations. And this time, maybe they're not geared where you can do it all of them, make the best sense. Sometimes we have to look at a problem and say, hey, I know there's 3 different ways. Which way is the best or which way is the easiest? Take a look at this one. I think substitution would be easier for 31. It already has a y equals. Take this y and plug the 2x in. Solve it. Back substitute to find your y. This next one here, take a look at it. There's no graph. Graphing is never the fun way to do these or the easiest. This one's already set up here for your x's to cancel. So elimination is much better on this one. Again, here's one. Elimination is much better. You should see that the y's line up. They're ready to go. And then you look at this one here and nothing. Oh, yeah, it does. Here we go. It says elimination. Your x's are good to eliminate. Hey, maybe you didn't see the x's were good to eliminate. What could you do to help you eliminate if you wanted to get rid of the y's? You can't add them, subtract these two together and make it go away. But if you wanted to, if it was a y that you were after, you could multiply this entire top equation by 2, and you could multiply this entire bottom equation by 5, and then your y's would cancel. Okay, so be careful when you do this problem. You need to first off see what's easiest when you're doing eliminations, but if you don't see it right away and maybe you choose the method that's a little bit more work, it may be a little more work, but you're still going to get the answer. Algebra is about perseverance. We have many ways to do things now. It's a big toolbox of information we have. You use the tools any way you like. Nobody can be there to tell you that you're wrong unless they're specifically asking you to follow a certain pattern and document each step in that particular pattern. Okay, this one said elimination, but it didn't say, well, what's the next step? They're suggesting to you to use elimination. If you would use substitution, would it still work? Absolutely. Don't be fooled by it. Do it your way. May not be the fastest way, but as long as you get the right answer, that's all that matters. Get busy, do that work, guys.